Ever wonder how scientists talk about Earth's history? I mean, 4.54 billion years is a long time. You can't just say, remember that Tuesday back in the Archean? Well, geologists have a system for this, and it's called the Geologic Time Scale. Think of it as Earth's grand calendar, a master timeline that organizes our planet's entire story. It's not just a list of dates. It's a narrative written in layers of rock, telling us about ancient continents, the evolution of life, and catastrophic events that reshaped the world. So, how do they decide where one chapter ends and another begins? Geologists are like cosmic historians, and they use specific clues to define the boundaries between eons, eras, and periods. One of the biggest clues is major biological turnovers. We're talking about mass extinctions like the one that wiped out the dinosaurs, or sudden bursts of new life, like the Cambrian explosion. These events fundamentally changed Earth's biosphere, leaving a clear mark in the fossil record. They also look for significant changes in the rocks themselves. This could be the appearance or disappearance of certain fossils, a switch from sandstone to limestone, or a huge gap in the rock layers called an unconformity, which signals a long period of erosion. These are the punctuation marks in Earth's rocky story. Then there are the chemical fingerprints. Scientists can analyze the chemistry of ancient rocks and find global geochemical signatures. For instance, a spike in the element iridium all around the world points to a massive asteroid impact. Shifts in carbon isotopes can signal massive changes in the global carbon cycle and climate. These chemical clues tell a story of worldwide environmental change. To get precise dates, geologists use two powerful tools: magnetostratigraphy and radiometric dating. Earth's magnetic field has flipped many times in its history, and these reversals are recorded in rocks. By combining this with radiometric dating, which measures the decay of radioactive elements in minerals like zircon, scientists can assign specific ages, in millions of years, to these boundaries. Finally, to make it all official, the International Commission on Stratigraphy designates a golden spike. This is a real, physical location somewhere in the world, a specific point in a rock outcrop that officially marks the boundary between two geological time units. It's the globally agreed upon reference point. All these methods combined turn Earth's chaotic, deep past into a structured, understandable timeline. The geologic time scale is broken down into 4 main chapters called eons. From there, it's divided into eras, then periods, and finally epochs. Let's start with the big ones, the 4 eons. First up is the Hadean eon, from about 4.54 to 4 billion years ago. The name Hadean comes from Hades, and for good reason. This was Earth's fiery beginning. The planet had just formed from the solar nebula and was being constantly bombarded by meteors. It was a world of magma oceans, differentiating into a core, mantle, and crust. Steam from volcanoes likely condensed to form the very first oceans. We have almost no rocks from this time, only tiny, incredibly tough zircon grains that have survived for 4.4 billion years. Next is the Archean eon, from 4 to 2.5 billion years ago. This is when things started to cool down and stabilize. The first pieces of continental crust, called cratons, formed, becoming the ancient hearts of the continents we know today. And most importantly, life appeared. The first evidence we have comes from microbial mats that formed layered structures called stromatolites. Early photosynthesis began, though it didn't produce oxygen just yet. Life was beginning to shape its home. Then comes the Proterozoic eon, stretching from 2.5 billion to 541 million years ago. This eon is a game changer. Around 2.4 billion years ago, the Great Oxygenation event occurred. Cyanobacteria had figured out how to produce oxygen through photosynthesis, and for the first time, our atmosphere started to fill with it. This was toxic to much of early life, but it paved the way for more complex organisms. We see the evolution of eukaryote cells with a nucleus and later, the first multicellular life, the strange and wonderful Ediacaran biote. The Proterozoic also saw massive snowball Earth events, where the entire planet may have been covered in ice. Finally, we arrive at the Phanerozoic eon, from 541 million years ago to the present day. Phanerozoic means visible life, and that's exactly what it is. This is the eon of complex animals, plants, and ecosystems. It's the one we know the most about because the fossil record is rich and detailed. The Phanerozoic is divided into three major eras: the Paleozoic, the Mesozoic, and the Cenozoic. Let's dive into the Paleozoic era, which means ancient life. It ran from 541 to 252 million years ago. It kicks off with the Cambrian period, famous for the Cambrian explosion. In a relatively short time, life exploded in diversity. We see the first animals with hard shells, like the famous trilobites. The Ordovician period followed, with even more diversification in the seas, and the very first primitive plants making their way onto land. It ended with a massive glaciation and the first of the Big Five mass extinctions. After that, the Silurian period saw the climate stabilize, allowing vascular plants to evolve and colonize the land, while the first jawed fish appeared in the oceans. This led into the Devonian period, the age of fishes, where fish diversity exploded. The first true forests grew on land, and our own distant ancestors, the first amphibians, took their first steps out of the water. Next, the Carboniferous period was a time of vast, tropical swamps. All that lush plant life eventually got buried and became the coal we use today. High oxygen levels allowed insects to grow to enormous sizes. Imagine dragonflies with the wingspan of a hawk. During this time, amniotes evolved, the group that would give rise to reptiles and mammals. The Paleozoic era closes with the Permian period. The continents had all drifted together to form the supercontinent Pangaea. Reptiles and our own ancestors, the synapsids, diversified across this vast landmass. But it all came to a horrifying end with the Permian Triassic extinction, the Great Dying. It was the largest mass extinction in Earth's history, wiping out about 96% of all marine species. This catastrophe paved the way for the Mesozoic era, the age of reptiles, or as you probably know it, the age of dinosaurs. It lasted from 252 to 66 million years ago. The first period, the Triassic, was a time of recovery. Life slowly bounced back, and among the new groups to emerge were the very first dinosaurs and the first tiny, shrew-like mammals. Pangaea began to break apart. Then came the Jurassic period. Dinosaurs became the dominant land animals, from the giant sauropods to the fierce allosaurs. The first birds evolved from small, feathered dinosaurs, and the Atlantic Ocean began to open up. The final period of the Mesozoic was the Cretaceous. Flowering plants appeared for the first time, changing landscapes forever. Dinosaurs like Tyrannosaurus rex and Triceratops roamed the land. The era came to a dramatic close 66 million years ago with another mass extinction. An asteroid impact, combined with massive volcanic eruptions, wiped out the non-avian dinosaurs and cleared the stage for the next group to take over. And that brings us to our own era, the Cenozoic era, the age of mammals, from 66 million years ago to today. With the dinosaurs gone, mammals, which had been living in the shadows, rapidly diversified to fill the empty ecological roles. The Cenozoic is divided into three periods. The Paleogene period saw the rise of modern mammal groups. Its epochs include the Paleocene, with the initial burst of mammal evolution, the Eocene, which was the warmest period of the entire era and home to early primates, and the Oligocene, when the climate began to cool and grasslands first started to spread. The Neogene period followed. The Miocene epoch saw grasslands expand further, which drove the evolution of grazing animals, and the first apes appeared. In the Pliocene, modern-style climates emerged, ice caps grew, and our earliest direct ancestors, the hominins, evolved in Africa. Finally, we have the Quaternary period, from 2.58 million years ago to right now. This period is defined by cycles of ice ages during the Pleistocene epoch. This is the time when our own genus, Homo, evolved and spread across the globe. We are currently in the Holocene epoch, the last 11,700 years of warm, stable climate that allowed human civilization to flourish. Some scientists argue we've now entered a new unofficial epoch, the Anthropocene, defined by the massive geological impact of humanity, from plastics and nuclear fallout in the rock layers to the dramatic spike in carbon dioxide. So, from magma oceans to modern cities, the geologic time scale is more than just a chart. It's the epic biography of our planet, meticulously assembled from rocks, fossils, and chemistry. It tells us how our world was built, how life conquered it, and how catastrophic events have repeatedly hit the reset button. By reading Earth's past, we gain the wisdom to better understand its present and maybe, just maybe, navigate its future. Thanks for watching, and don't forget to follow for more stories written in stone.